Assalamu alaikum. So last week we started our new topic of analyzing unsymmetrical beam bending problems, and basically we saw how there were two main assumptions in our Mechanics of Materials 1 course, which we are relaxing one by one for our more complicated analysis in Mechanics of Materials 2. So the first assumption that we had in MOM 1 was that we were just looking at symmetrical cross-sectional shapes. And the second one was that we were assuming that the applied bending moment was about the neutral axis. So last week we had relaxed our first assumption and we had started to look at beams with arbitrary cross-sectional shapes. That means that we could have either symmetrical or unsymmetrical shapes. And basically we saw how we can analyze any cross-sectional shapes bending given that we follow a set of or a series of systematic procedures. इसमें we saw that what we have to do most importantly is that we need to place our establish a right-handed coordinate system very carefully. And what we need to do for it is that we put our origin at the centroid of the beam cross-section, take our x-axis to be coming out of the beam, and then we have our y and our z axes of our right-handed coordinate system aligned with the principal axes of the shape. And if we do that, then we see that we can use basically our flexure formula directly for this beam bending problem. Right? So we can use our flexure formula अगर हम ये सारे series of steps follow करें for even our unsymmetrical shapes. Okay, so that was the discussion last time. Today, I want to move on to relaxing our second assumption and assume that hamari bending moment can be applied about any axis even other than the neutral axis. So for example, let me consider for just the simplified purposes, let me consider a rectangular cross-sectional shape. And let's consider अब ये rectangular cross-sectional shape का मुझे पता है that it has an axis of symmetry, these two axes of symmetry. So my principal axes will be of course aligned along and perpendicular to these axes of symmetry. So I've established my right-handed coordinate system according to the rules I'd established in the last lecture. But now this time around, what I've basically got is that I've got an applied bending moment M, which is acting about some arbitrary axes in the YZ plane or in the cross-sectional plane, not just about the Z axis. पहले तो हमारे सिर्फ Z axis के along moment act करी थी, अब वो आप देखें किसी inclined axis के along act कर रही है. So इस किस्म की situation में हम उनको किस तरह beam bending को analyze करते हैं. Basically what this problem then involves is that we need to resolve our applied bending moment along the y and the z axis and then look at those individual components separately and then finally apply the principle of superposition. Okay, so that's the series of steps that we will be following. Let's just go through these one by one in more detail. So as I've said, I've got a problem in which I have my bending moment M acting about some inclined axes, not about the Z axis. ठीक है जी. तो अब इस किस्म की situation में as I've already mentioned कि I've properly established my right-handed coordinate system such that x-axis is coming out of the beam, origin is at the centroid, the y and the z axis align with the principal axes, with me following the convention that the z-axis is the principal axis with the maximum moment of inertia. ठीक है जी. So once I've done all of this, then मुझे bending moment M की problem को define करना शुरू करें. Let me define the angle first. Okay, this bending moment M actually takes an angle of theta, is at an angle of theta from the z axis. Okay, so that I'm defining this theta to be positive going from the plus z to the plus y direction. ठीक है जी. So इस direction में मैंने theta को positive consider किया, from the plus z to the plus y direction. And if I do that, then I can use straightforward the resolution of a vector along particular directions to find कि इस total applied bending moment m का क्या component है in the z direction और क्या component है in the y direction. That is, if I draw out the components, the individual components, I get my mz, which is the resolution of this vector along the z-axis, to be just equal to m, the magnitude of the applied bending moment, times cos theta, क्योंकि वो base से correspond कर रहा है उस triangle के. So mz is given to me by m cos theta, and then the y component my is given by m sin theta, which would correspond to the height of the triangle. ठीक है जी. तो स्ट्रेट फॉरवर्ड वेक्टर रेजोल्यूशन हो रही है, या फिर इन अदर वर्ड्स हेड टू टेल रूल करें अगर मैं इन दोनों कंपोनेंट्स का, तो फिर आई विल गेट माय नेट अप्लाइड बेंडिंग मोमेंट. राइट. And now that I've got my individual components, then I can apply my flexure formula for each of these, because मेरे y और z axis principal axes के along aligned थे. Okay, so then of course my total stress at any given point on the cross section is given by the stress arising because of mz, okay, and the stress arising because of my. So I just need to add those two longitudinal bending stresses together. So mz की वजह से जो स्ट्रेस होगा और my की वजह से जो स्ट्रेस होगा, और दोनों का अपने अपने जो stresses हैं, those are given to me by the flexure formula, such that the total normal stress acting at any point on the cross section is given to me by this expression right here. Flexure formula से bending stress arising from my, and flexure formula से bending stress arising from mz and from my. ठीक. Let's take a look at what the individual components in here are. So sigma is the longitudinal normal stress at any point on the cross section. Any point in the cross section जो कि किसी coordinates के साथ होगा. Let's say I'm considering the stresses right here. Then this takes the coordinates of y comma z, noting that these are the coordinates along the principal axis. This is important कि मेरे y और z axis principal axis के along ही align है. And then this my and mz are the respective components of the bending moment. And finally जो iz है और iy है, वो मेरा moment of inertia है about the y axis and about the z axis. ठीक. So of course अगर मैं खाली mz को consider करूँ पहले, तो अगर if I'm looking at mz, I know कि mz की वजह से जो bending stress arise करेगा वो flexure formula से given है. लेकिन उस flexure formula की अगर मैं right hand grip rule करते हुए देखूँ कि अगर मैं एक plus y coordinate पे हूँ, let's say इस वाले coordinate पे हूँ जो plus y पे है, तो उस पे क्या stress act कर रहा है, tensile या compressive? Then please, if I use my right hand grip rule, pointing my thumb in the direction of the moment, of the vector moment, then the curl of my fingers is giving me the direction of the turning effect or of the stresses. So if I use my right hand grip rule, I can see that for plus y's, मेरी fingers actually अंदर की तरफ curl हो रही हैं, such that at this point I get a compressive stress due to mz. ठीक है. Let me repeat. Pointing the thumb in the plus z direction, I can see कि when I curl my fingers, वो इस point के लिए plus y के लिए compressive हैं, वो into the beam जा रही हैं. ठीक है. तो वो compressive होने की वजह से I have a minus right here. Whereas अगर if I perform the same procedure for my my component, to consider कि ये जो मेरा point मैंने लिया था this time around, क्योंकि अगर मैं y से stresses देख रही हूँ, then I'm looking at the z coordinate, y-axis से देख रही हूँ अगर, then this time around if I use my right hand grip rule, I can see, and pointing my thumb in the plus y direction, curling my fingers of my right hand, I can see कि वो इस z point से बाहर आ रही हैं fingers. That means that the normal stress caused by my at this point is tensile. Hence why for the my component ka normal stress I have a plus right here. And finally just noting कि जो bending moment consider की जा रही है, for example my के लिए I'm interested in the moment of inertia about the IY axis. So my problem के लिए I need the IY and I need the coordinate from that axis. Hence why वो जो flexure formula है let's say कोई भी coordinate मैं उसको दे देती हूँ, MA divided by IA होता है, let's say उसका magnitude, पॉजिटिव टेंसाइल या कंप्रेसिव जो है मुझे राइट हैंड ग्रिप रूल दे रहा है, देन आई एम कंसिडरिंग कि अगर मैं एम वाई को देख रही हूँ तो देन आई हैव एम वाई, कोऑर्डिनेट उससे क्या है, जेड कोऑर्डिनेट है वाई एक्सिस से, और मोमेंट ऑफ इनर्शिया क्या है अबाउट द वाई एक्सिस, दैट इज आई वाई. And then finally right hand grip rule say I know that that is a tensile stress for this point, hence why ये पूरी की पूरी term आ जाती है. And similarly for the mz component, that is bending about the z axis. So I have a bending component of mz, my coordinate is y, and finally the moment of inertia is iz that I'm interested in, and using my right hand grip rule I can see that it's actually causing a compressive stress at this point, hence why there's a minus right here. Okay, so the total stress arising from my actual applied bending moment M is due to the stress arising from its individual my and mz components. Perfect. Let's actually try to draw these stresses out, the individual stresses. So for example, if I'm looking at the normal stresses arising because of mz, तो वही अगेन हमने अपना राइट हैंड ग्रिप रूल को यूज़ करते हुए हमें पता था कि टर्निंग इफेक्ट उसका कुछ ऐसे कॉज हो रहा है, दैट इज़ वो उस एक्सिस से अबव, जेड एक्सिस से अबव कंप्रेसिव स्ट्रेसेस है और जेड एक्सिस के बिलो टेंसाइल स्ट्रेसेस कॉज कर रहा है. लेट मी से कि ये जो मैक्सिमम वैल्यू है ना विच फॉर दिस एम जेड कंपोनेंट, उसका नाम है सिग्मा एक्स मैक्स. ठीक है, और दिस इज़ द स्ट्रेस प्रोफाइल फॉर जस्ट फॉर एम जेड. फिर अगर मैं एम वाई का भी बनाऊँ, दैन एम वाई के लिए बेसिकली यूजिंग द राइट हैंड ग्रिप रूल, आई नो using the right hand grip rule, I know that it causes tensile stresses to the left of the y-axis and compressive stresses to the right. इसके कर्ल से पता चल रहा है. ठीक, अगेन ये सिर्फ इंडिविजुअल कंपोनेंट्स का है. जो टोटल स्ट्रेस स्टेट होगी दैट वुड बी गिवन बाय द सम ऑफ दीज टू स्ट्रेस डिस्ट्रीब्यूशंस. ठीक है, आई विल ड्रॉ दैट आउट इन जस्ट अ सेकेंड. सेकेंड थिंग आई वॉन्ट यू टू नोट इज़ के इंडिविजुअल कंपोनेंट्स के लिए फ्लेक्चर फार्मूला अप्लाई हो रहा है. फ्लेक्चर फार्मूला अप्लाई होने का मतलब ये है कि अगर हम जेड एक्सिस वाले एम जेड के स्ट्रेसेस देख रहे हैं तो वो अबाउट द जेड एक्सिस से लिनियरली इंक्रीज़ करेंगे क्योंकि फ्लेक्चर फार्मूला अप्लाई हो रहा है. सिमिलरली वाई एक्सिस वाले जो बेंडिंग मोमेंट है उसके स्ट्रेसेस भी वाई एक्सिस से लिनियरली इंक्रीज़ करेंगे because the individual components are given by the flexure formula. However, the total resultant stress state is caused by the sum of these two, और उस sum को then draw करें अगर तो we just add together these two stress profiles to get something like this. So for example, what's happening is that let's say if I look at this corner right here. Now at this corner I can see that because of my mz I'm getting a compressive stress, and because of my my I'm also getting a compressive stress, such that their two effects add up and I get a larger total compressive stress acting at that point. Correspondingly, अगर if I look at this corner, I can see कि इस corner के ऊपर mz की वजह से एक tensile stress है और my की वजह से भी एक tensile stress है, such that at this corner I get a total larger tensile stress. Okay. Finally, ये बाकी दोनों corners के ऊपर mz और my के opposite sign stresses हैं, right? एक टेंसाइल है, एक कंप्रेसिव है, जिसकी वजह से इधर ओवरऑल इफेक्ट कम हो जाता है from the individual effects, right? Such that from this I can see कि जो largest compressive और tensile stresses हैं वो actually opposite corners पे act कर रहे हैं. So एक corner of the beam पे largest compressive stress है इधर और इस corner के ऊपर largest tensile stress है. So they are acting on opposite corners. और जो दो दूसरे corner रह गए इस किस्म की बीम के लिए एटलीस्ट उनके ऊपर कोई स्मॉलर मैग्नीट्यूड नॉर्मल स्ट्रेस एक्ट कर रहा है. Perfect. Okay. So that this is basically my total stress distribution drawn out right here. Now looking at this, I can also spot that there is actually some points on the cross section जिनके ऊपर zero normal stress हो रहा है. Now of course this exactly the points on which there is no normal stress or there is zero normal stress, they are the points that lie on the neutral axis. Hence why I've labeled this line right here as NA, which is then giving me the neutral axis. So I can find the position of this neutral axis simply by substituting in a zero normal stress in my expression for the total longitudinal stress in the beam. That is वो जो मैंने पहले अपने सिग्मा की एक्सप्रेशन निकाली थी उसमें बस सिग्मा इज इक्वल्स टू ज़ीरो डाल दूँ. ठीक है जी. फिर if I manipulate this so that I get y in terms of z, then I get this expression. इसको rearrange कर दिया. Now noting right now कि I already know what my my and my mz are in terms of the applied bending moment m. Of course my जो mz जो था that was m cos theta and my जो है वो m sin theta है. तो उनको मैं substitute कर दूँ अगर इस expression के अंदर, then I get this slightly more simplified expression right here. लेकिन actually हम इसको मज़ीद simplify भी कर सकते हैं. Let's think about how to do that. So this expression right here, y is equals to this term times z. Note what's inside here. So iz or iy जो है geometric properties हैं of the cross section. For a given cross section, these two are constants. Tangent theta जो है that's the property of the applied bending moment. Loading की एक property है. So for a given problem, that's also a known value. Hence why this is actually a constant, right? So this is actually y is equals to kz. So agar I draw out my axes, which were something like this, y इधर था और right hand grip rule की वजह से z की positive direction ये थी, given के x is coming out, then this y is equals to kz equation जो है that's the equation of a straight line like this. ठीक है. अगर मैं इस एंगल को इस स्लोप को डिफाइन करूं एज लेट्स से अल्फा, ठीक है जी, देन आई नो दैट टेंजेंट अल्फा is actually equal to, what is tangent alpha equal to? The height y divided by the base z. So tangent alpha is equals to y divided by z, right? So let me rearrange this so that I get my y divided by z on one side. Then that gives me that this alpha right here is equals to tangent alpha. Sorry, that tangent alpha is equal to that y divided by z. So rearranging this expression so that I can get y divided by z, to get tangent alpha, I get that my basically the orientation of my neutral axis from the plus z axis is given by this expression right here. Iz divided by Iy tangent theta. Right? So once I have a given problem, that is मेरे पास एक given cross section है, I can find my Iz and Iy, एंड फ्रॉम दैट गिवन प्रॉब्लम मुझे मेरी बेंडिंग मोमेंट की ओरिएंटेशन भी पता होगी कि वो बेंडिंग मोमेंट किस एंगल पे अप्लाई किया जा रहा था. सो आई देन नो टेंजेंट थीटा, सो दैट मैं उनको सब्सटीट्यूट करके ये टेंजेंट अल्फ़ा को फाइंड कर सकती हूँ. दैट इज़ फ्रॉम दिस आई कैन डायरेक्टली फाइंड कि किस एंगल पे मेरा न्यूट्रल एक्सिस लाई करता है, which will enable me to draw it out more clearly or to see the problem more clearly कि कहाँ पे zero stresses हैं. Right? Please note very carefully in this that this tangent theta, so this theta and this alpha are two completely different physical things. So theta was the angle of the applied bending moment and alpha is the angle of the neutral axis, both being defined positive from the plus z to the plus y directions. Okay, so ये दो फर्क चीज़ें, you have to be a little careful about this. Okay, so just to summarize the entire procedure for unsymmetrical shapes and for arbitrarily applied bending moments, what did we do? So first of all, we established a right-handed coordinate system with the x-axis coming out of the beam. We placed our origin at the centroid of the cross-section. We aligned our principal axes, we aligned our y and z axes along the principal axes of the beam, following the convention के the z-axis corresponds to the largest moment of inertia. ठीक है, ये convention को follow करना ज़रूरी है. And if we do that, then we can straightforwardly decompose our applied bending moment or resolve our applied bending moment into its respective mz and my component to get the sum of the normal stresses arising from these individual components to give us the total stress distribution on the cross-sectional plane given by this expression right here, जहाँ पे I went through the detail के ये individual terms का क्या मतलब है और कहाँ पे compressive stress है, किस component की वजह से compressive stress है और किस component की वजह से tensile stress है. So please note कि if you want to I'll come to this note in just a second. And finally, इसी bending normal stress की expression से हम the position of the neutral axis को भी निकाल सकते हैं, which is given by this expression right here, that tangent alpha is equals to Iz divided by Iy tangent theta. Ab, you will be, some of you of course have a tendency to memorize things, so let me make it explicit कि if you do that, you need to understand कि ये कहाँ से आया था. The reason being that these expressions are only true if you have followed all of the conventions that we have discussed. That is, ये सिर्फ आपको यही रटी रटाई expression अगर आपने use करनी है तो आपको वही right handed coordinate system को उसी तरह place करना है जिस तरह हमने discuss किया है, y और z axes की उसी convention को follow करना है, theta और alpha की उसी convention को follow करना है, and so on. ठीक है? Only then these expressions only hold true for the procedure that we have followed. Okay, that was key. Otherwise, because essentially if you understand what's happening, which is के individual moment components के लिए flexure formula apply हो रहा है, then it's very straightforward for you to analytically write this down yourselves, the expression for the normal stress. Whereas the position of the neutral axis, this will be provided to you. Okay, so sorry, let me repeat this last point. Sigma x will not be given to you, so not given for whatever examination purposes. I know कि आप लोगों को सिर्फ उसी से गर्ज होता है अक्सर, इसलिए this will not be given, so you need to understand कि ये कहाँ से आ रहा है और कैसे आ रहा है. Whereas this the expression for the neutral axis, position of the neutral axis, will be provided. And the reason for this is Okay, the expression for the normal stress is just arising because of an understanding of how the flexure formula can be used for this unsymmetrical problem. Whereas the neutral axis, fine, I don't want you to have to unnecessarily memorize things. Okay, so that is the main summary of this unsymmetrical beam bending. In the next lecture that I will have uploaded as well, the numerical examples are being solved. So please go through them in your own time. Thank you.